Okay, so this video we're going to look at the other type of remainder, the other type of error. And this comes in when we're doing any other Taylor polynomial or Maclaurin polynomial. The one we learned in the other video can only be used for alternating series. That would be converging. So this is called the Lagrange remainder, or it's also known as the Taylor remainder, Taylor theorem remainder, or Lagrange error, I guess you could call it. So it's similar to the alternating series remainder, where we're going to use the next term to find part of the error. So the Lagrange remainder, so if we look at the two, the only difference here is this z and c. So we used the c value in the first one. Okay. This z value is a little different. So it's an x value between your x value that you're evaluating and your center. So you have to pick a value, and so it could be between or it could be on one of those where your function would be at its maximum value. So it'll make a little more sense once we see some examples. Okay, so that's what that goes through, so you can read that later. So estimate e squared using a Maclaurin polynomial of degree 10 for e to the x. All right, so remember we would have to write out a Maclaurin polynomial, which we can either write it down or remember. So we have 1 plus x squared, okay, divided by 2 factorial, or just 2. So we have all of those laid out. We have 3 factorial and so on. So if we go all the way to 10th degree Taylor, so we have x to the 10th over 10 factorial. Okay, so that's going to be our Maclaurin that we're going to use, and we're going to evaluate this at 2. So x is 2 because we want e squared. So e squared is going to be, we'll just plug in 2 to all these values here. So we have 1 plus 2 squared over 2, and so on down the line. Okay. So plugging these in, so 2 to the 10th over 10 factorial would be our last term. So we're going to go ahead and plug these in. Okay, and everything in between, so we can't forget those. I just wrote it out this way just because it is a pattern that is repeating. If we calculate this, we're going to get 7.38899. All right, so it's adding all these terms together. It's a little pain, but it's not too bad. So that's what our estimate is. Okay, so that's it for example 6. So that's something we've done before. We've created a Maclaurin or a Taylor, and we've evaluated it and gotten an estimation or an approximation for our function. So in this case it would be e to the x, evaluated at 2. All right, sorry. All right. Example 7 says use the Lagrange form of the remainder to estimate the accuracy of this partial sum. So we're going to take a look at the e to the x again, and we're going to find the Lagrange error. So Lagrange remainder is always a maximum. So we have the error is going to be less than, or the remainder will be less than or equal to the absolute value of, so we went to the 10th degree in example 6. So we're going to do the 11th degree for the Taylor. So we go ahead and we plug in our number we were evaluating at. We're going to go to the 11th power. Just like we were doing up here, we're following this pattern. And we're going to go over 11 factorial. Okay, so we just follow the pattern for the Lagrange remainder. The difference here is what we're going to multiply the top by. So we're going to multiply the top number by some maximum value for the function. Okay, so if we think about so Maclaurin, we're at 0 for our center. If we go between 0 and what we're evaluating, so 0 and 2, what's going to be the maximum value of e to the x? Well, we know e to the x is it's a exponential growth. It's growing. It's increasing. So are we going to be at a maximum at 0 or 2? Well, it's going to be 2 because we're growing as we approach 2. So this value that has to go here, we're evaluating our function at e squared. Okay, so e squared is the maximum value that e to the x can attain between 0 and 2. Okay, so this part right here is kind of the tricky part of all of this. Everything else is pretty straightforward, and it's not very helpful that the maximum value is e squared. I mean, we're trying to come up with something that we can calculate fairly simple, but we would have to use a calculator for e squared. But it is what it is. So we plug this in and we find out that the error is, let me see, 0.9804. Actually, no, that's, sorry. It's 0.000379. Just jumping ahead of myself a little bit. So that's our remainder. Okay, so it has to be less than or greater, or less than or equal to the 0.000379. Okay. So I would write something down about this e squared being the maximum value of that function between 0 and 2. Has to be at 2. Hopefully that makes sense. If not, get with me and ask questions. All right. So let me go back a little bit and clarify. So e to the x, we're talking about the derivative, which we know is just e to the x. So this is the maximum value of the derivative. I think I said that before, but I just want to make sure. All right. So moving into example 6, or example 8, we have 2 examples left. Okay, so if f, so fifth derivative is 700 sine x, and x equals 0.7 is the convergence interval for the power series centered at 0. Okay, so all this says we're centering at 0 and we're evaluating at 0.7. Find the upper limit for the error when the 4th degree Taylor polynomial is approximated for f of 0.7. All right, so the Lagrange remainder. Remember, absolute value. We're going to the next term. So we were dealing with the 4th degree. Now we go to the 5th degree. We're centering at 0 and evaluating at 0.7. So we have 0.7 to the 5th power over 5 factorial. And now we have to calculate this maximum. So we need to think a little bit about this. So if we look at the the fifth derivative, okay? That's 700 sine x. So sine of x, maximum value of sine. So let's think about this. So back in trig, we talked about max and minimum of sine and cosine. So the maximum value for sine or cosine would be 1. All right? So that's nice when we're using this idea of Lagrange remainder when we're talking about sines and cosines. It makes life a lot easier. You don't have to calculate anything. We just have to think about sines and cosines having a maximum of 1. So if sine has a max of 1, okay, so let me write that down. Sine of x, max value is 1. You might want to make reference to that somewhere. Okay, so sine is 1 max, and multiply that by 700. So the maximum value that our fifth derivative would be is 700. So that's what we're putting in there. Okay. We calculate this out, and this is the 0.9804. Okay, so that is the Lagrange remainder for this. All right, so let's go ahead and plug these in. So we have a 6th degree. Okay, so 6th derivative. If the 6th derivative, that's what that means, is a positive decreasing function, so we're going down, find the error bound when a 5th degree Taylor polynomial centered at 4 is used to approximate f of 4.1. Assume the series converges at, or for x equals 4.1, okay? So this one, what we're doing is setting up Lagrange remainder. Oops. Got a little crazy there. Less than or equal to okay, so 5th degree Taylor, so we're going to the 6th derivative. So we have our 6th derivative evaluated at 4, so our center. And why we chose 4, so think about it. It says it's a decreasing function, so between 4 and 4.1 we're decreasing. Our values are getting smaller. So the maximum for the 6th derivative would be at 4. So that's what we have to evaluate at. Okay, that's going to be the max. Multiplied by, and we're going to, our x value is 0.1. That's what we're evaluating at, because remember it's the x value we want minus our center, so 0.1 difference to the 6th power all over 6 factorial. Okay? So maybe write that down. I'm not going to write it out, but make a note of that. Between the center and the number we're evaluating at, so center and x, what's the max value? So it's 4 because of the decreasing function. Okay. All right, so that's it for this video and the section. So go ahead and try the work. There are quite a few hard problems in here, so just make sure you reach out and let me know if you need any help on them.